So we had a little bit of stuff left over from last time, like 5 slides or something. And we're going to finish that and then segue into the next stuff, which just continues on it. So we're talking about isotopic fractionation in carbon, hydrogen, and oxygen isotopes. And we ended up last time looking at the kind of ranges of standards and stuff is compared to and the values that we see in different systems on Earth. And there's a couple of things that fall out of all the stuff we discussed about, such as the hydrologic cycle, is, evaporating and precipitating and making solid and stuff. It involves a lot of isotopic fractionation, especially of that kind related to the velocity of the molecule. So as you can imagine, we get isotopic heterogeneity in various reservoirs in the hydrologic cycle, and it's super dependent on temperature. So if you go to the polar regions, you're going to see different fractionation than you see in the equatorial region. So there's something that we call the meteoric water line, which is basically the relationship in oxygen isotopic variation versus hydrogen isotopic variation, and how that falls out throughout the hydrologic cycle tells us something about the conditions of evaporation precipitation now and in the next sense. And we'll look at that in what's coming up in what's going to be the lecture for today. But this just shows you, as kind of a prelude to that, oxygen isotopic composition relative to that SMO scale. Remember, SMO is the ocean. These are in delta units relative to temperature, right? So this is just going up in the atmosphere, sampling some water, and you can see there's a big variation between, cold locations and warmer locations. And that's recorded in the water. And we're going to see that, as I say, in a second, in things that come back out of the hydrologic cycle. They tell us something about temperature plus minus latitude. So this is another kind of effect that happens. So when we evaporate stuff out of the ocean and we make atmospheric water, there's a fractionation associated with that velocity difference of the heavy and light isotopes, water molecules made of the heavy light isotope. Then, when that stuff, we nucleate clouds, we start to make rain, we have another isotopic shift, right? And so this stuff gets enriched in light isotope during the evaporation process. In a relative sense, this gets enriched in heavy isotopes during rain, right? The rain is still less than the water in the ocean, right? So that this effect is stronger than this effect. Nevertheless, that's sort of a transition of what happens. And as the water vapor laden atmosphere with storms kind of migrates across the landscape, the rain comes out progressively, right? And so we first initially favor heavier isotopes in the formation of the rain, leaving the cloud lighter. So as we move along, the cloud continues to get lighter and the rain also gets lighter. Okay. Actually, I said that wrong. The rain should get reflectively heavier as it continues along. But the point being that every step in the process causes fractionation. The fractionation reflects the conditions. And so when we want to try and use this information as what we call a paleoproxy to pull back information from the past, we have to understand a lot about processes. So what we kind of learned by looking at fluctuations in Earth's climate, which again, we'll talk about as the main topic today, is that what really happens is not so much that the whole planet gets warm or gets cold, it's that the gradient of temperature going from the equator to the poles is more or less steep. So that during a kind of a very warm period, for instance, in our current last couple of million years where we've been fluctuating between ice ages and interglacials, what makes an interglacial is that the temperature at the pole gets a lot lower, right? The temperature at the equator doesn't change all that much, pretty much never, maybe by half a degree to a degree. But what really is happening is that as you march northward or southward along latitude lines up towards one of the two poles, you're either going on a shallow or a steep gradient. And we see that in the water that's evaporated from the oceans. So if we're near the equator, right, where it's relatively warm, we get isotopically heavier water. You recall, when the temperature is higher, the fractionation of a lot of isotopes, the distinction goes down because there's more energy in the system. So the evaporation of water is mostly a function of enriching the atmospheric water in the lighter of the two isotopes. But more so, the colder the temperature. So if you go up to the poles, you get more isotopic fractionation. And when you get to the equator, you get less. This is relative, but if you add to that the fact that during glacial interglacial cycles, this curve is more or less steep, this curve also gets more or less steep. And stuff that comes out of the hydrologic cycle during an ice age is going to reflect more of a difference as we go from the equator to the poles, and then during a warm time such as today. If the planet heats up a huge amount because of anthropogenic impact, then we expect this gradient to go down even more, to become more flat. Does that make sense? Okay, so this is this thing called the meteoric waterline. It's a plot of the delta O18 oxygen and the delta D, which is the hydrogen isotopic composition. Okay, and there's an equation for the line. It's called the meteoric waterline. This was something that was worked out in the 50s, and it's held since then. Right? If you look at water that just came out of the atmosphere, it conforms to this line. Okay? And it's not just water in the atmosphere like rain, but it's also surface water that hasn't interacted too much with sediment. We look at runoff here in Hawaii, it fits on this line. The place where it starts to deviate from the line is when you start to have interactions of water with rock, like weathering processes. So if you make clay minerals or something like that, you also can fractionate these isotopes, more so the oxygen and the deuterium. So you can see here this sort of little area of rock, of water, and these are water that sits in places where it's being fed by groundwater that has spent a long time in the ground. So you get a slight shift. Okay. So, and this is basically a view of a variation in the northern hemisphere in precipitation. So this is stuff coming right out of the atmosphere. And again, you can see, this comes from the textbook, you can see all these things, but then hopefully if you know your geography, you'll know where some of these places are, right? Like places that are near the equator, places that are cooler, they fit along this line. And that's just sort of average temperature during the year. It does affect the precipitation in the water. So another thing that happens, if you recall when we talked about rain, we talked about the marine salts, and when you're over the oceans, you have a lot of that in the rain, and then when you move across the landscape, it goes down. Right? The same thing kind of happens in the isotopic composition on average of precipitation over continents. So this is North America, and it's contoured for the oxygen and hydrogen isotopic composition. In one of them is in parentheses, and the delta D is the big one, and the one in parentheses is the delta O18. You can see that the rain, you can see here how this number is going up, and this number is going up. So the rain changes as we go through the landscape such that it evolves, right? Because the source of the water is over the oceans, seawater, whatever, big storm systems come across the continent, and they're progressively raining out more. There are water. When they're raining, they're fractionating. And so there's the initial fractionation, which is to make the atmospheric water. And then as we move it across the continent, if we were to dump all the rain at once right at the coast, then there wouldn't be a huge amount of fractionation. But because a lot of storm systems evolve slowly over the landscape, that fractionation process is manifested. So the farther we get in from the coast, the more isotopic effect we see. So another thing that happens is exchange of meteoric water with rock at high temperature. So this is a meteoric water line again. These black dots are surface water sampled in areas that happen to have geothermal activity. Okay? And they all fit on this line, right? And they kind of reflect what comes out of the atmosphere. So this is the geothermal place in New Zealand. You know, we have Iceland. This is also Iceland. This is Northern California. This is Steamboat Springs. It's like, I think it's Wyoming or Montana. It's not somehow near Yellowstone, you know that. So see these open symbols that have a shift in the oxygen isotopic composition, but not this. These are waters that interacted in the ground with hot rock. The hot rock shifts the oxygen isotopic composition, makes it closer to smoke, right? So it erases some of the isotopic heterogeneity that the rainwater has in it that form the meteoric water, which ultimately circulates in the ground to make groundwater. There isn't much shift in hydrogen, so things move along this line. Just because there's proportionally way less hydrogen in the rocks And even though there would be an isotopic fractionation, it doesn't show up in a net sense because there just isn't that much to exchange with. There's so much hydrogen in the water, not very much in the rock, that you just don't really see a shift. So water gets shifted along horizontal lines, and people can in fact look at water in different locations, compare the geothermal water to the surface water, and using the hydrogen isotopic composition, kind of put it on this line and then figure how far off it's been shifted and say something about the temperature of that resource and or the amount of mixing between hot water in the ground and water that has been heated up. So that's just a shift that happens due to high temperature. So that was the end of last time. So now we're going to move on to the main thing, which is how we use isotopes in paleoclimate. So that's what we're going to do today. And then next time we'll use all the information gathered from understanding isotopic variations along with some other stuff, which we'll also talk about today, some other kinds of paleoclimate records. And then we'll look at, what that tells us about how the carbon cycle and climate have been linked together over the last, various periods of time in Earth's history, and what that bodes for sort of future climate and something about the science of that. So something that I'm sure most of you know is that we've had warm periods and cold periods on the planet, right? And most of the time when the planet gets cold, it also gets dry, also gets windy. Something that we know, we can see greater proportion of dust-based deposits during cold period of time, like ice ages, for instance. So if you go into a cold period of time, right, like an ice age, you enhance the global oxygen-16, oxygen-18 fractionation during pretty much all the processes that happen in the hydrologic cycle. This cold temperature increases isotopic fractionation. You do the same thing for hydrogen deuterium, but we're going to mostly focus on that. Go to a warm period of time, you subdue the fractionation. So imagine you go back into the past to a period of time where we had no ice anywhere. We had no continent over Antarctica, over the South Pole. And what we would expect during those periods of time when there was no glaciation on the planet is less variation between the oxygen-16-18 ratio of stuff that interacts with the hydrologic cycle around the globe as a function of geography. We go into a cold period of time to expect more variation. Does that make sense? Okay, so we get more isotopic fractionation during cold periods and less isotopic fractionation during warm periods. Okay. So in essence, we can use the oxygen hydrogen isotopic composition of water that's been interacting with the hydrologic cycle as a thermometer. There's some caveats, there's some things we have to avoid, like water is exchanged a lot with rocks. It might have, as we saw in that last slide with the last lecture. There are other complications as well, but the main thing is if you can reconstruct in an accurate way time and location, so geochronology to date deposits, location, if it's not too long ago, the location is probably the same, but if you go further back in the past, you got plate tectonics, you got to move stuff around on the globe. But if you can do those two things, then you know how to interpret oxygen hydrogen isotopic variations as a function of temperature. Then you can start to decipher past climate on Earth, past temperature variations. And so this is the hard part, is kind of figuring out, well, how do you get that from this? There's all sorts of extra complicated secondary effects. Some of that we'll talk about today. And so, like in a lot of other aspects of science, there's things that we're really confident about, there's things that we're pretty confident about, and there's things that we're not as confident about. The things that we're very confident about are how temperature affects these kinds of things, and what kinds of secondary effects might throw things off. Like if we go to one site, we get values that are really weird, we can think through and look at other things in those materials to decide that. There's always uncertainty in geochronology. There can be uncertainty in recovering temperature. But then on top of that, we also have to make sure that there's some other like non-temperature related effect. And one thing that we have to be worried about, as we'll see in a moment, is that when organisms are involved in making archives, like little shells that we get out of sediments, they can overprint the isotopic fractionation that happens in nature from this. we have to be a little bit concerned. And it turns out, different organisms or different species of the same organism can have a different oxygen isotopic shift. For instance, when they make a shell, we call it a vital effect. We need to correct for all that stuff, right? And all that stuff has uncertainties. Nevertheless, uncertainties are not big enough to obscure the original signal. So I already showed you this slide again. I just want to from last time, I just want to remind you that there is this fractionation that happens throughout the hydrologic cycle that involves the initial event of evaporating water out of the oceans and following up after that with precipitation. So now I want you to think about, all right, we know we've got, at least for the time being, a big ice sheet in Greenland, right? We have some sea ice that forms in the northern hemisphere in the wintertime, getting less and less each year, and we have the ice sheet over Antarctica. All of that ice reflects the state of the hydrologic cycle. Now, the sea ice is complicated because it comes from the seawater below it. So let's just take that out of the equation for a second. We'll treat that separately later. But the water that went through the atmosphere and lands on the ice sheets, that experiences this kind of fractionation. Okay, so if you think about ice sheets and you think they're at high latitude where the fractionation is the most, and they're reflecting in a net sense the water that's evaporating out of the oceans, moving farther away from the equator and then raining back out and forming the ice that accumulates in the ice sheets, what we can say is that during periods of time in the past where it was colder, like ice ages, we store more water in our ice caps, right? Because they get bigger. And that water shows more of this isotopic signature that we expect to happen during cold periods of time. Both the original evaporation of water from the ocean and the temperature effect of making it. So at colder times, we favor light isotopes in the atmospheric water, which means our ice sheets get bigger and the water gets isotopically lighter. Okay? And during warm times, we have less water there and it gets isotopically heavier. And so we want to know both of these parameters. We want to know the temperature signal in the oxygen isotopic composition. We also want to say something about volume, because the amount of water that goes into an ice sheet is water taken out of the surface oceans, right? So as you can imagine, you get your oceans here and you're evaporating some water and you're moving it up and you're depositing it in a glacier, then not only is the water in the glacier reflecting what came out of the atmosphere, but the ocean has lost some water that is the complement of that, the mirror image of that. So we want to be able to do a mass balance, and we want to be able to say how much water was taken out of the ocean and how much did it affect the oceans at the same time as we're affecting the ice sheets.
When it says during warm times, less H2O is stored, does it mean more in the oceans? It says less and then less. Wouldn't it be more?
Yes, you are correct.
Okay.
That is a typo. That should be more.
Okay.
Absolutely.
That's what I figured.
Fix it right now, just so that I don't forget. Thank you. Paying attention. Yeah. So this is an ice core, and ice cores in a lot of settings, not every setting, but they show a seasonality. Yeah, just like sediments, they don't necessarily always deposit at the same rate. In a lot of, especially in the northern hemisphere and Greenland, you can see layers of dust that separate the annual periods of time. Because during the summer months, there's a lot more dust deposition and not much ice deposition. So that kind of shows up. And the way in which, ice is formed from things like first snowfalls, and then the snow continues to accumulate and it compacts. It makes something called firn, which is kind of a granular, high porous ice. And then with compaction, as you go further and further down, it turns into ice. That process can take like a decade, right? So the upper part of an ice sheet is complicated, especially today because we got all this melting going on. But when you go down into it, a little bit down, this is just a drill core that's been sliced in half. It's been illuminated from the back so you can see it. You have this annual band, right? People can count the bands and figure out the years. And there's all sorts of other cool stuff that happens in ice cores, like you can measure the chemistry of the water. And one of the things that you see is during periods of time of extensive volcanism, you can find spikes of acid and spikes of oxidized sulfur, as we already talked about with the sulfur cycle. That's a different thing. So we know that today ice sheets on the planet make up something like 2%, right? If we go back into the ice ages, it was more. Okay, and it depends on which period you want to look at. Some of the glaciations were bigger than others. And if we go back further beyond the Quaternary, there were other periods of time of ice on the planet. So if you want to get a continuous record, right, you want to go to a place where there's pretty much always ice, like Greenland, right? As far as we know, there's always ice. You wouldn't want to do this measurement at what was the edge of an ice sheet, because then there might be gaps in the record, which are harder to deduce. But you can actually tell things like, was there melting or something like that, or compaction, or even things like internal motion within a glacier that can displace things as it flows and stuff. And so people have recovered kind of like the perfect records in both the northern hemisphere and the southern hemisphere, and done this stuff, counted up the layers, measured the water, looked at the oxygen composition, and they see fractionation variations that we know. Okay, so in essence, this is like a super simplified version of what the polar ice record looks like. It's this brown line here. As we go back and forward in time, the oxygen isotopic composition, this is the heavy isotope, right? That goes up and it goes down. And hopefully it makes sense that this goes up during a warm period of time. During a warm period of time, there's less isotopic fractionation between the light and the heavy isotope, and the evaporation of water favors the light isotope. So when it gets warm, we favor the light isotope less, and when it's cold, we favor the light isotope more, right? So that shows up in this signal. Now, think about, as I mentioned previously, the seawater that's left behind, it gets the mirror image signature. So it turns out that the evaporation happens out of the surface ocean, not integrated throughout the entire ocean over the time scale at which this happens. Remember, the oceans circulate on a 1,500-year time scale. So mostly the signature of evaporating water and fractionating the oxygen isotope shows up in the surface water, and surface seawater has a mirror image look to it. And the way we know this is that things living in that seawater, such as organisms that make calcium carbonate shells, precipitate that shell in equilibrium with the seawater. And so we can look at stacks of sediments, where we can date them and look at their time variation as well. We can see these kinds of patterns. This is just a picture of a marine sediment, and that's obviously ice core. Okay, so this is a reconstruction of the Delta 018 ice from Vostok, Antarctica, so southern hemisphere. And this is depth going back into the core. So this is like a 2,000 meter or 2 kilometer thick core. It's a pretty big core. And people have correlated it back in time. This is one, what we call glacial interglacial cycle. So here's today, and here's something in the past. This is the peak of the last ice age, what we call the LGM, or last glacial maximum. Okay, and this is going further back in the past. We are currently, if you just take human activities out of our current climate, we are in what's called interglacial period, a relatively warm period of time during the glacial interglacial cycle. This was the last interglacial period. Its peak was about 125,000 years ago. Sea level was a little bit higher than it is today, and we know this because the whole Evo Plain, which is a coral reef, was deposited during that time. It's called the Waimanalo Formation. And you need to be a little bit shallower to be able to make coral reef is now above sea level, unless the island is lifting out of the water, which it's also doing a little bit. But the key point here is that there's oxygen isotopic variability. You can see these are really negative values on a smoke scale, right? It's really light compared to standard mean ocean water. All the water that evaporates from the ocean is going to be lighter than the ocean it came from, but it's a question of, is it really light or just very light, right? We're going between minus 55 and minus 60 here. And that's pretty early work. If you want to go further back than that, though, right, you have to find other archives. So it turns out that, let me just go back there for a second. You can find ice in parts of Antarctica that go back almost to the prior interglacial, which is about 210,000 years ago. But to find that really old ice and the probability that it hasn't, as it's been flowing along, kind of deformed and messed up, and you've got some complications, somewhere through the ice stack, it gets harder and harder. So there are ice cores since this was published that take this record further back, but they're not very good. And they only take us back one more cycle. If you want to get all the cycles, even in the Quaternary, the last couple million cycles, you got to find a different marker. If you want to go back to something like, well, what was it like in the Cretaceous? Ice isn't going to do it. So that's where we switch to marine sediments. And that's where this is important, right? Because what we see in ice and what we see in marine sediments are going to be a mirror. Okay, so this is a delta 018 now relative to the PDB scale. That was that shell that some guy found in North Carolina and compared everything to. This is fluctuation over a pretty long period of time. It goes into the latest Paleocene. Okay, and so almost all the way back to the Cretaceous, not quite. Maybe back to about 50 or 55 million years. What you see, okay, is a delta 018 record, and then there's a temperature. This is an interpretation, okay? And there's a lot that goes into converting this into temperature. We don't have a ton of time to go through all of that today, but it depends on many, many factors. But what we see in general, hopefully you can see the overall shape of this curve, is that going back in time over the Quaternary into the Paleogene, is that oxygen isotopic composition goes relatively heavy and relaxes back towards zero, right? So we're looking back in the past. I like to think about stuff as the Earth moving forward in time. So back in the past, before we had Antarctica over to the South Pole, when the planet was a lot warmer, and as we'll see coming up, CO2 in the atmosphere was way, way higher. Right, similar to what humans are doing to it now. We had a much warmer planet, and across the entire planet, we didn't have any ice sheet. And when we evaporated water from the ocean, it was hotter, so we made it isotopically heavier. Okay, so if we evaporate water from the ocean, we make it isotopically heavier. We leave the ocean, in a relative sense, isotopically lighter. Okay, so that's why this gets lighter into the past. Because we were favoring, because it was warmer, we were favoring more evaporation of heavy isotope. Okay, so now if you come forward in time, you can see, this kind of spiky curve, and there isn't much resolution here. Again, this is an early record, so there aren't very many data points. But what you see is that there's a period of time where, it's changing a lot, and maybe not so much, and changing a lot again. There's been a lot of action, in the Pleistocene and the Pliocene, which reflects global climate and ice sheets of the configuration that we currently have. So these are kind of some zoom ins. This is all from marine sediments, carbonate sediments of the shells of organisms that live in the ocean. Okay, and so here's the last sort of 4 million years. Okay, again, wiggles of the delta 018 on the PDB scale between 3 and 4. So it's kind of like 1 unit of delta 018. And in case you're wondering, we can pretty routinely measure this unit to like 0.01. Right, there are specialized facilities that can do it even better than that. But this is not uncertainty in the measurement. We can measure that pretty quickly. Does anyone know? See these names here: Mariana, Gauss, Gilbert. What those might be? Heard of those? Do you know how the magnetic field on Earth goes back and forth? Right. So people have named the excursions between the field being like today, and then the field being the opposite polarity, and then flipping back, and these are the names. Okay, and so the last period, major period, is called the Bruns. It's not even on here, but the Bruns-Mariana boundary is a famous layer between the last time there was like a major flip. So this was like the opposite polarity, and then this was the back to the original polarity. And within these periods, the core, the way it rotates and the way it generates a field can cause flipping. So it's sort of the dominant form of, what does the field look like predominantly during this period of time. And that's a way of getting some time information out of sediments. You just run a magnetometer down it. You don't have to do any geochronology, because part of the kind of plate tectonic revolution that allowed people to put stuff together was the advent of geochronology and the mixing of it with the paleo magnetic records to figure out time scales pretty quickly. Okay, so what you see here is that this is younger, this is older. So as you come forward in time, right? There's still not very many data points in here, but hopefully you can see that the value is higher and less variable and gets lower and more variable, right? This is the development of quaternary climate that we now experience, where we have ice ages and warm times. We've had that for a few million years, but the intensity of it has gotten stronger over time. Okay? So now if we zoom in even more, this is just the last 700,000 years. Okay, so that's a tiny little slice. And again, this is the delta 018, but notice how this is on a SMO scale and this is on the PDB scale. So the absolute values are going to be different. You can convert between them. They're like, you know, there's an equation which we'll talk about in a moment too, but I also showed it to you last time to exchange between them. And so what you see here is that there's this set of wiggles that goes up and down, up and down. Here's today, here's the last ice age, here's the last interglacial when the Wymanala Formation was formed. So this is what we call one glacial interglacial cycle. Here's the one before it. It doesn't look exactly the same, but it's got a lot of similarities to it, right? It's got an ice age, and it's got a warm time. And we go back further, we got an ice age, and it's got a warm time. It's got an ice age, and it's got a warm time. And hopefully there's a few things you can notice about it, which is that as the warm times going into the ice age takes some time, right? It's about 100,000 years. To come out of ice age into a warm time is fast. It's about 10,000 years. And that's been recorded pretty much all the way through. You can go all the way back here. See the same thing. Slowly developing into cold and then shooting back out. And so this tells us something about how the planet responds to whatever forcing is causing this to happen. Natural forcing is causing that to happen. And you can see here that the isotopic variation, regardless of which scale you're on, in the shells is something like a little bit more than 1 part per thousand, right? 1 ppt. So here we go. That's 0 and 1. So, you know, whatever that is, that's not quite 2. This is 3 and 4. And again, you know, and that's the current variation. So even if you didn't have a ton of resolution, or maybe you have like a mixed sediment or whatever, you measure a bunch of measurements and you see less variation, then you're probably looking at a period of time in the past when the climate didn't operate the way it does. Okay, so it turns out that to get temperature from that information, you can just measure oxygen isotopes and be happy with it, but if you want to reconstruct temperature, then you need to know how do organisms who make shells fractionate calcium carbonate. So first off, there's an inorganic process that happens independent of organisms, and we talked about that a little bit before, right? That can be parameterized for the formation of calcite. Let's just say we're sticking with foraminifera. We're not going to look at pteropods, which make aragonite. People have worked out this expression, which says that the temperature at which the fractionation happens is constant minus this equation, right? And it's a second order polynomial. And so delta C is the delta oxygen 18 value in the carbonate minus the water it grew in, right? And so we see that again here to the squared with a different constant current. So in essence, what it's telling us is that we can deduce temperature from the difference between the isotopic composition of the carbon and the water, right? So it's a little bit hard. We can measure this. We can measure the carbonate, but we don't get to measure the water. So we have to make some inferences about it, right? Which it means comparing various sites and estimating how much water varies today as a function of evaporation and precipitation through a glacial and glacial cycle. Okay, now on top of this, there are biological factors that are species specific on this equation. They represent a permutation on it. This is what happens if you just make calcite from water. So if you allow organisms to do it, think about all the metabolic phenomena that an organism does. It takes in food. It takes, if it's a respiring organism, it's going to take in oxygen and breathe out CO2. There's forming and breaking of bonds. Even if it's a, you know, a photosynthetic organism where it's going to take CO2 and do primary productivity and put out CO2. All of those processes fractionate oxygen from isotopes from each other and carbon isotopes from each other, hydrogen isotopes from each other, and not all organisms do it exactly the same. So on top of all that, we have to know, like, oh, this specific species of shell, you know, someone's grown it in a lab and it can measure how it fractionates stuff. And so when people make these kinds of reconstructions, They're usually based on a handful of species that we know behave really well. We know that those shells, when they're falling down to the water column and get to the sediment, they preserve well, right? We don't have to worry about a lot of dissolution that's happening because of the CCD. And so there are, and it's widely distributed. So there are certain species that are common for these kinds of reconstructions because we find them all over the planet. We find them going back in time in the past. We find that they have a predictable isotopic fractionation from what we call the vital effects. And we find that they're relatively well preserved on the seafloor. So this is another foraminifera record. These are planktonic. And so it's important to know these terms because I've already been using them, but planktonic means living up in the water column. Benthic means living near the seabed. This is, when we talk about a planktonic foraminifera record, we're talking about the photosynthesizing plankton that lives right up in the photic zone in the water column. Okay. And so if you go back into the past, right, this is 2 million years, this is basically the Quaternary record. These again are the magnetic reversal of time scales on there. This is what's called a stack record from a bunch of drill cores all around the planet. People have picked out their favorite species. And then if one lab's measuring one species of foraminifera, another one's measuring another, they can make a shift because both of those species have been calibrated to how much fractionation they put in. And then what you see is a series of wiggles, as we've talked about before. We're in the modern epoch, which is stage 1, called marine isotope stage. Oftentimes now in the literature, you'll see people just say MIS. That stands for marine isotope stage 1, which is where we are now. The last ice age was MIS2. The last interglacial was MIS5. Okay, and so how these things get numbered, I don't know who got together and decided on this, but they alternate between warm and cold periods of time. And some of these numbers refer to the transitions, right, coming out of a warm period into a cold period. But some transitions don't get numbers. But the system is pretty consistent. And hopefully what you can see is that as we go back here till about 700,000 years, there's a kind of wiggle that kind of changes. Okay, and we'll talk about why that changes in a moment. But the forcing function changes the way this looks, the thing that's making climate vary in the first place. And we go further and further back in time, again, we see less variation and less kind of really easy to recognize periodicity, right? This looks a little bit messier than this, okay? But there's obviously an oscillation there. Okay, so this is some of the stuff that goes into reconstructing a record like that. So this up here is a plot of the delta O18 in planktonic foraminifera, the photosynthesizing organisms that live in the photic zone. And on the same thing in yellow are benthic foraminifera, okay? Things that live near the seabed. You can pick those things out, and people who know what their species are can look under a microscope and pick out shells and say, okay, here's my pile of planktonics, here's my pile of benthics, I'm going to measure oxygen in 18 of them. The curves look pretty similar, right? But notice the absolute values. These are a lot lighter, these are a lot heavier. Okay. Which in part reflects a lot of stuff about like how the ocean circulates and how water masses separate. But on top of that, remember the surface ocean where these dudes live is the stuff that's being evaporated to make the ice sheet. So it's feeling the hot, cold climate variations. And this is 100 centimeters, 200 centimeters, so that's 0.2 meters. This is one glacial interglacial cycle. Modern, last ice age, modern. Okay. And so we look at benthic and planktonic to tell us different things. Planktonic tells us about the surface oceans. It preserves a lot of geographic variability. Benthic tells us something more integrated about the whole ocean and that whole oceanic conveyor belt of circulation and all that kind of stuff and mixing. And so, we might want to say, oh, well, so how fast was ocean circulation going during the ice age? Deep water masses and stuff. We can look at the offset between these two curves that are scaled and see that there's a bigger difference during the last ice age, which means the water was flowing more quickly, right? So however that trend, we don't know anything about the geography of it and stuff, but all other things being equal, there was more freshening of deep water masses and all that entails during ice ages recently than during non-ice ages. So here's this plot here. I don't know if you can see it, but these are two different foraminifera. okay? Two different species. And on the same scale, we get different isotopic shifts in it, right? This is -1, that's 0, that's +1. So this organism, when it grows, it happens to make a heavier shell than this one. This is stuff that's been determined in the lab. And so a person can go and look in a record and pull out the shells of this organism and this organism. When you do an oxygen-isotopic composition at this level, you can just do one shell, right? You don't have to do a bunch of them. People will do multiples just to sort of compare and look at uncertainty and so forth, but it's not like we need huge piles of material. And so we see a mirror image, the same exact record, but there's a shift. And so to make what's called a stacked record, where we're looking at a bunch of different sediments from different places and presumably different, individual organisms, people have to make all those corrections. And then they average them out and we get something like this. Okay, so now here are some other what we call paleoproxies. This is just oxygen-isotopic composition in some shells. This is the delta O18 in the water in the Greenland ice sheet, as we've already talked about. It has that same sort of signature to it. Warm, coming down into a cold period, shooting back up into a warm period. This is pollen in the Mediterranean region. Pollen that has been turned into an index of how many trees are there. Okay? And again, that is somehow a function of how wet and how windy the climate is. And apparently during warm periods of time, you get a lot more of this stuff. And during cold periods of time, like the ice age, you get a lot less. This is plankton living in the North Atlantic, not their isotopic composition, but the organisms themselves, which also reflect temperature in the water color. And this is a calculation of variations in our albedo. We'll get to what this means in a second, but this is basically different amounts of light presumably reflecting off the planet. We weren't there to measure it, but based on the kinds of things that cause light variation off the planet kind of being calculated and assumed. And like I said, we'll look at that in a second in more detail. So now this is a diagram in the Atlantic Ocean of sediment cores going down with depth. This is at 42 degrees latitude. It's not like the tropics or anything like that. Relatively northerly, kind of New Yorkish. And this is 78 degrees. Okay, like up near into the Arctic Circle. These are a bunch of cores in the North Atlantic. Now, the North Atlantic is this place where we make that cold water and it sinks down in the bottom of the ocean basins and flows along. So we see things in that water that if that process changes, we're going to see it recorded here. But that's in the deep water masses. In the shallow water masses, there's a pretty strong temperature gradient through the North Atlantic, which reflects processes such as how the circulation happens and how climate varies. Okay, so now this is color coded or stipple coded, I guess I would call it, for 4 things, which is the assemblage of organisms that live there: polar, subpolar, transitional, and subtropical. Okay, and so without doing any oxygen isotopes or anything else like that, you can see that when you go down through these cores, if you go up into the Arctic Ocean, you always have polar stuff, right? And as you go further to the south, in some periods of time, you start to pick up these subpolar species in a warm period of time. Sometime in the past, water was relatively warm, so we managed to get subpolar species all the way up here at 74 degrees. As we go further south, this essentially what we see is that warming of the assemblage, right? But also flipping back and forth. Doesn't matter which stack you go through, you find more than one assemblage, which means that the water mass above this place where sedimentation is happening is changing its temperature enough to change what organisms are living there and fall into the seabed. So you can take that information and you can reconstruct what you think the temperature profile in the upper water column was. And on the basis of that, you can try to infer where you think ice sheets were in the past. Okay? There's another indicator we have about ice sheets, which are that ice sheets that formed on land and then extend offshore carry with them at their base little bits of rock that they carved off the landscape. And when that gets out over the ocean, and then that ice melts, it drops all those little particles. We call them ice-wrapped debris, or IRD. So you can go back into sediments like this, and you can find little periods of time where you have high probability of finding IRDs. There are these warm periods of time. So the species assemblage changes, and we get these little particles, sometimes called Heinrich events, when we find high amounts of IRDs. So this is a reconstruction of surface isotherms in the North Atlantic today-ish, right? This plot's about 20 years old, but there's North America, there's Africa, and that's actually Europe, that's England and Scandinavia. And so you can see what the temperature was. And this is a reconstruction back into the past during the peak of the last ice age. And so you can see here, like down here is the Horn of Africa. You can see a 22-degree isotherm. And over here, it's 26. So it's some variation, but not a huge amount. And what you find, as I mentioned before, is a steepening of the gradient, meaning in the ice age, you go through a lot of isotherms very, very quickly as you go up northerly, and over here you have less, right? So you can see this sort of packing in of isotherms. That's this gradient. So from that, people can reconstruct ice volume changes, and this is just a graphic showing, well, that's what ice looks like, kind of quote unquote today, meaning 20 years ago, pre-anthropogenic. Well, it's not pre, but a lot less anthropogenic signal. And this is what it looked like during the last episode. And you can do this ad infinitum further back in time. This is a composite of satellite data from something called the IPCC Intergovernmental Panel of Climate Change. It's a UN-sponsored organization. It's been working since the 80s to make reports about the climate status on the planet. This is, from one of they do these reports like every 5 to 7 years. So this was the one in 2013. There actually was just another report that came out a couple of years ago. And they don't always put in the same stuff. But so this is basically the yellow line is the average of ice sheets between whatever it says here, 1979 to 2012. Right, so just the average. And then the snapshot, the photo, is what it looked like in 2012. And I think you can see it looked a lot smaller in 2012. If we were to do this today, it would look a lot different. And this is during the time of maximum melting, during the summer, right? That's where we're basically seeing, so this is land ice on Greenland. This is sea ice. We're seeing the sea ice go away. We'll have ice-free Arctic probably within the next decade. And that, of course, people are talking about it. It changes, all of a sudden ships can go from here over to here and this kind of stuff. And there's a lot of geopolitics going on. If you look in the southern hemisphere, you don't see that much variation. So I don't know if you can make it out with your eye, but this is the Antarctic Peninsula, and this is I'm following the coastline of Antarctica, right? And then this is sea ice. So when this is maximum melting, this is maximum accumulation. And you can see here that the yellow line matches up pretty close with the other stuff. It turns out that on the southern hemisphere, the things that cause ice to form and not form on annual cycles hasn't varied as much. There are variations we can see here in the thickness and the rate of motion of glaciers, but where we're seeing the biggest effect, especially in sea ice, over the last several decades is up here in the northern hemisphere. So now we can go back into past climates and we can say, all right, there's a bunch of stuff we can look at. You can look at the distribution in various records of things like your aquatic fossils. You can look at pollen and terrestrial records. You look at the type of sediment that's being deposited and the grain size. Remember that thing I mentioned about it being windier or not. You can look in your ice core records back at least a certain period of time. And you can look at the distribution of glacial deposits and landforms that we find on the planet. Terminal moraines, glacially exposed surfaces, which can be radiometrically dated, those kinds of things. And measure oxide isotopic composition in materials and do what we call paleothermometry. And what we kind of find is that during periods of time when there are glaciers and not glaciers, interglacial periods of time, the maximum temperature swings we find are about 5 to 7 degrees C, right? That's about the maximum amount. And so when people talk about, oh my gosh, it's going to get warmer or colder, or how warm or how cold, we kind of know at least how much the Earth varies. And this doesn't seem like that much, right? It's like, oh, the difference between 80 and 85. It's still a warm day. But when you integrate it over the whole planet and you can or can't make ice, for instance, at certain temperatures, it ends up being really important. These are big, big temperature variations. And what we find, as I mentioned before, is the gradient of temperature between the pole and the equator. So while on a global basis, we might have a couple of degrees of temperature change, up near the poles is changing even more. The poles are really sensitive, and that's where the ice is. Okay, so when we look at past climates on Earth, we can deduce a lot of stuff. As we go further and further back in time, we have less and less resolution and stuff. So this is like yet another record of the glacial interglacial cycle. I apologize, but sometimes these plots have modern over here, and sometimes they have it over here. This one happens to have, this is modern, this is going back. Okay. This is record converted into temperature. Okay, and so what we have is warm, cold, last ice age, getting back to warm, the prior ice age, and further back. Okay, and this is the last 160,000 years. Now this piece of the puzzle fits in here. If we look in records that go further back, like marine sediments, we basically see this pattern roughly repeated here and here and here, et cetera, going back. This is a million years ago. Okay. Now look at this plot. This is the longest time period of time. This goes back to 180 million years. So this plot fits in here, right? This plot would be some tiny little wiggle right up in there. And so what you see as you go back in time, the same thing that we just said previously a few slides ago about the oxygen isotopic composition, is the temperature changes from being very variable, like up and down, and colder, and we get further back in time, at least over the time scale of this, it gets less variable and hotter. Okay, so last time that Earth had no ice sheets over either of its poles was back up in here. And that's why it's called the hothouse. There's a ton about why Earth was that way back then, and it isn't today, but a lot of it has to do with where were the continents and how were the oceans circulating. How were we being heated by the sun has varied a little bit, but not that much. It's really about how does the whole oceanic circulation and atmospheric circulation system work. And when we didn't have a continent over the South Pole, things worked a lot differently. The oceans worked a lot differently, especially before we started to break up continents and move them along. We were in a period that people call the hothouse, right? I don't know who came up with that name, but it's kind of cool. And at some point in time, as we got into the Paleogene, we went into something called the ice house, right? That means a whole planet which is susceptible to cooling and can make glaciers, big glaciers, ice sheets. And as we move forward in time, that gets more and more intense and more variable, right? So culminating in today, which is periods of time over this sort of 120,000 year cycle where it goes ice age, not ice age, ice age, not ice age. But it wasn't always like that. And we didn't just flip a switch and go into it, we transitioned kind of slowly into it over several million years. Okay? So there's a lot we can infer. We'll talk next time about, oh, well, what's the carbon dioxide content of the atmosphere back here where we had no ice sheets? Unfortunately, we've already blown past it as far as we can tell, right? So this process reflects things that happen kind of slowly, the geological progress of things, millions of year time scale, the Earth is in equilibrium, whatever's changing causes it to have these different periods of time. Here we are, it's like 200 years, we're like, let's change the CO2 from a condition like that to a condition like that and see what happens. That's basically what we're doing. So there's a lot of non-equilibrium processes going on right now that make it complicated for us to predict the details. Not the basics. We know the basics, right? And climate deniers spent decades trying to convince us that we didn't know this stuff. We know this stuff. We don't necessarily know all the little details. Okay, but so as implied by its name, fourth ice house, that's not the first time on the planet where we had a configuration of stuff that allowed us to grow ice. It's the fourth time, right? And there may be others that are obscured in the geologic record, but periods of time into the geologic past, as described here, where there was significant ice accumulation. And part of the way they know that is like, oh, look, here's a terminal moraine, or here's some, a glacial deposit that we're finding, especially in marine sediments, where they find these IRDs, the ice-directed debris near the equator. So, periods of the Permian, periods of the Proterozoic, where we had glaciation. There were other periods of time where we had no glaciation, right? And people have reconstructed that. And so we know that, like, for instance, this period of time that we're in now, which we've been in for a few million years, it's not the first time that's happened. Okay, so that's an important component of stuff. So now we have to think a little bit about, all right, what makes the planet hot or cold in a relative sense? And I showed you this plot early on in the semester. I want to show it to you again. This is the heat coming in from the sun to the planet, right? In red, and in green is the heat being radiated back out, the albedo, the stuff that's being reflected. So here's the equator, that's the North Pole, that's the South Pole. So on average, we get more heat from the sun in radiant light near the equator and less near the poles, right? And because of a combination of the transition from short wavelength to longer wavelength, plus heating of the oceans and water masses circulating and moving along and transferring heat from the equator up to the poles, the stuff that reflects back out shows less variation. Shows variation, but it shows less variation, right? And so there's a budget between how much heat comes in and how much is reflected back out. We get a surplus at the equators and we get a deficit at the poles. And if you think back to what I said about there being a gradient between ice ages and warm times, between how hot it is at the equator relative to the poles, right? What we're really looking at is a change in this curve. Something changes the balance. And there are factors that reflect how much light reflects off the planet and in what wavelengths. There are factors that reflect how much ocean currents are and atmospheric currents are redistributing heat content that all go into making a reconstruction. But the net effect is that during certain periods of time, this deficit gets big enough that over the poles, we grow ice sheets. And during other periods of time, this deficit gets a lot less and we have a lot less ice. If we go back further enough in time into the Cretaceous, this deficit wasn't enough to be able to have an ice sheet over the southern Hemisphere. So this is another plot from that IPCC. I've shown you a plot just like this. It's not quite as cool of a colorful infographic. But this basically shows you of all the incoming solar radiation, how much of it in the visible wavelength, how much of it bounces off in different wavelengths. Some of it, remember we talked about this before, something like 2/3 of it comes off in the infrared, 1/3 bounces back out in the visible, some of it bounces off the clouds, some off the land surface. And this stuff is, the atmosphere is not transparent to it. So whereas it's transparent to the visible light, things called greenhouse gases, which we've talked about before, and we'll talk about again next time, absorb some of this heat, right? So there's what we call positive feedback. So in periods of time where the atmosphere holds more of these gases, which happens to be warm periods of time, then it can store more of its heat. And when it does that, that affects, that affects this energy balance and how much of a surplus and how much of a deficit we get. Okay, so this shows you something called the atmospheric window, right? Turns out that even though in the infrared wavelengths, we know there's absorption going on, we know what molecules are doing the absorption, right? So in our natural atmosphere, water and CO2 do the bulk of the absorbing of infrared radiation, warming the planet. In general, that's a good thing. It helps modulate climate on the planet, helps make the planet be habitable. Just compare what the temperature extremes are at this distance from the sun by going to the moon where there's no atmosphere. You see these wide temperature swings. It wouldn't be that, it would, you know, if they had an atmosphere with water and CO2, it would be like that. So it turns out that there are a lot of wavelengths that of light that are absorbed by water and CO2, and they're kind of shown here. But this is the percent absorption of our atmosphere. But there are also parts of the atmosphere where there isn't so much absorption, right? And so you can also see a couple of other important chemicals. You can see oxygen and ozone. Okay, so if we come up into this little zone, this is visible over here. This is the wavelengths where the main heat absorption happens, right? We can see this area, this kind of zone where there isn't as much absorption. And it turns out that us changing our atmosphere in various ways is narrowing this gap and filling it in. So this is where, you know, it's already absorbing 100% over here, right? We can add more stuff to the atmosphere. We can't absorb more than 100% of the heat in that wavelength. But when we fill in this window by putting gases into the atmosphere that increase their concentration, then we make the atmosphere better at holding heat, right? So less of it reflects out into space, which helps make it hotter on the planet. Okay, so this is another plot. It's a simplified plot of just that atmospheric window. These are 4 greenhouse gases that humans are putting into the atmosphere and changing the amount of absorption of heat. So we can see what happens with the carbon dioxide we're adding. Basically, what it does is it just brings this already existing CO2 peak down. Okay, it's warming the planet, but things that are warming the planet even more are chlorofluorocarbons, which are also destroying the ozone layer. Ozone, which we produce in the lower atmosphere with automobile exhaust, and nitrogen oxides, which we produce by over-fertilizing farm fields and then having the nitrogen come off the landscape. All of those absorb in the infrared and fill in this atmospheric window and contribute to the heating. Okay. So, as I mentioned before, we're going to look a little bit at the variability. Warm periods and cold periods on the planet reflect this change in the gradient between the equator and the poles. It doesn't change all that much at the equator. Maybe a degree or so between ice ages and cold periods, but it changes a lot, maybe as much as 10 degrees up here. So you can say, well, what are all the stuff that can make temperature change on the planet? There are controls that are off the Earth, like, oh, maybe the sun is changing how intense it is on some frequency. Maybe the Earth is changing how it orbits the sun, which if you know the story already, you know that that's the main driver. We can have other kind of random things like big meteorite events, impacts. Then there's things that happen internal to the Earth that also affect the climate, like global tectonism. The long, slow progress of the continents, the breaking up of supercontinents, the making of mountains, all that kind of stuff over millions and millions of year time scales does affect climate. That, internal variations is what makes this period of time look different than that. But it takes tens of millions of years for that to happen. And that's been cranking over Earth history, and that has a lot to do with how rock weathering, in a relative sense, affects CO2 in the atmosphere. During periods of mountain building and lots of excessive rock weathering, we pull CO2 out of the atmosphere and we cool it, vice versa during periods of time when things are relatively flat. We also have volcanism, puts gases in the atmosphere that both absorb heat and reflect heat. And then we have the biosphere, right? Big changes in the biosphere can also affect CO2 in the atmosphere and the thermal conditions. But the most important thing is to ask yourself, well, which one of these things is cyclic, right? Because we've seen that our climate variations are cyclic. They go back and forth on a regular rhythm. And pretty much the only one of them that is cyclic is this one, on the right time scale. There is cyclicity to solar intensity. There's a sunspot cycle, this kind of stuff. It's not enough to cause the temperature variations, and it happens over way too short of a time scale, right? So as far as we know, Earth orbital fluctuation is the main thing causing the climate variability that we see, okay? And so this just kind of reviews some of that, like the plate tectonic cycle, how volcanism works, and pretty much everything on that prior slide is random in time. It doesn't have cyclicity except for Earth's orbital parameters. And those are called the Milankovitch cycles, named after a mathematician who kind of calculated based on orbital parameters what the various wiggles and wobbles in Earth's orbit around the sun might be. In 1870, it was made more kind of precise in the 30s. And basically, this is what it looks like. There are 3 different aspects of the way Earth orbits the sun, meaning the eccentricity of our ellipse, how big it is. The Earth has a tilt towards the sun of its axis, and that tilt kind of changes. Then we have a wobble, which is called precession, which is basically, when we're tilting away from our elliptical plane, is that tilt towards the sun or away from the sun? It's just the kind of the wobbling of thing. Each one of these things has a periodicity to them. A 20, a 40, and 100,000 year periodicity. They add together to tell us how much temperature variation we get on the planet vis-a-vis this thing, right? So if the Earth is exactly perpendicular to the sun, its tilt axis, we get a different distribution of heat as we go from north to south hemisphere than if it's tilting northern hemisphere towards it or northern hemisphere away from it. We get an imbalance in the southern in northern hemisphere is a function of how much that tilt and that wobble progresses. So that's basically the gist of how someone calculates something like this, which is a northern summer insolation. Insolation is the term of how much heat do we get from the sun. This is how, in theory, it varies in time as a function of these three parameters. There are a lot of estimates that go into here. It depends on what latitude you make this estimate for. But in any event, you can calculate that. You can compare this with actual records from, oxygen isotope proxies or paleotemperature proxies or hydrogen isotopes in ice cores or whatever you want, and you see a ton of alignment. This is what's forcing, in a collective sense, climate variations on the planet today. If you go back in the periods of time where we didn't have ice ages and warm periods of time, the Earth was still doing this stuff. It's just that the configuration of things, the other driving factors, configuration of the oceans, configuration of the continents, amount of rock weather, put us into a period of time where we just weren't sensitive to these. So the ice houses, the period of time where we do go between warm and cold periods of time, are relatively few and far between on the planet, and they reflect having the right conditions. So these are, again, the three frequencies in the Milankovitch cycle, and these are 4 or 5 different proxy records. This is CO2 in the atmosphere. You can reconstruct CO2 by melting ice, and we're seeing how much gas it liberates from ice sheets back at least a certain period of time. This is tropical sea surface temperature. This can be estimated in a variety of ways, but usually with the strontium-calcium ratio of calcifying organisms like corals and our skeletons. Back in time, this is a temperature reconstruction. This is benthic oxygen 18 records and benthic foraminifera, and this is sea level. All of them show basically the same things. They go high in the same places, they go low in the same places, and they reflect the integrated combination of these three things. Not exactly, but pretty close.
That's kind of scary. They're looking at line C and obliquity, how it's projecting for the future. We're having smaller scale changes.
Well, right. So what happens is this one here happens to go through these kind of like periods of time with less and periods of time with more.
When it's less, carbon's way higher.
Yeah, it's like I said, there's a lot of stuff going on.
Yes, there is.
So it turns out that when you kind of figure out how to go from having sunlight hit the planet to having a climate that fluctuates, we have to go through the filter of the biosphere. Because most of the gases that are causing the absorption of greenhouse gases, CO2, methane, nitrogen as N2O, they are all modulated by organisms. Not so much us, but things like all the phytoplankton in the ocean or all the tropical rainforest. So part of this fluctuation is driven by how much light is coming from the sun. But superimposed on that is, what does the biosphere do? So if the biosphere is cranking, meaning we got a lot of photosynthesis, a lot of respiration, we're putting a lot of gas in the atmosphere, the planet is able to warm up. So at warm periods of time, where less of the planetary surface is covered by ice and can't grow anything, we put more gas in the atmosphere. So it's warm because the solar insolation. But it gets even warmer because we put more gas in the atmosphere, and the atmosphere is able to absorb more greenhouse gas. When we go into the cold period of time, the opposite is true. It's cold, and there's less CO2 and less methane and less N2O in the atmosphere. So the atmosphere itself, from the perspective of gases, is not able to hold as much heat. So you can say, well, which comes first? Is it the solar insolation or is it the gases? And so this is a careful reconstruction of carbon dioxide, methane, and temperature in ice sheet from Vostok, okay, which is southern hemisphere ice. And what you find, this is today, this is the last ice age, that's the last interglacial, the prior ice age. You have to look in very carefully, and this temperature reconstruction comes from the oxygen and hydrogen isotopic composition, the meteoric waterline, which I introduced this topic today with. Is you see that the gases do what we call lagging. They follow the temperature change, right? So the planet starts to change a little bit because of the solar insolation. That cranks up the biosphere. The atmosphere is able to hold more heat, and that's part of what makes this ascent from an ice age into a warm period so fast. It's the combination of atmospheric forcing plus greenhouse gases. This is all natural. Now, superimpose on that human activities, which have already, and we'll talk about this more next time, but the amount of CO2 that we know we have in the atmosphere here to here, you can see the numbers here. They're about 175. This is just, about 280. Okay, we've now taken it up to about 450, right? So the amount of change that we've done in a couple hundred years is of the same magnitude that happened naturally over a period of about 10,000 years, from the last glacial maximum to the start of the Holocene. And you can see how much temperature variation that did, right? That did, something like 3 or 4 degrees. So this is part of how we can say, well, we're putting some CO2 in the atmosphere. This is how much warming we think it's going to be. This is kind of what it comes. Okay, so there's a few other things that kind of want to go through quickly, which is the time scales over which this happens. And the time scales reflect two things: how fast all the processes that modulate gases in the atmosphere change, and their reservoir sizes. So this is a depiction of the carbon cycle, the amount of methane and CO2 that exchanges between the water and the atmosphere, and how much is stored in the water, how much is stored in rocks and land plants and everything else. And as we've already talked about before, there's a lot of carbon stored up in the oceans, even more in oceanic sediments. There's a bunch on the land. There's very little in the atmosphere comparatively. But all we have to do is change something about the balance of this, or the rate at which gases exchange between various things, and we can start to build up atmospheric gases. Right, and some of these processes are slow. So this is a compilation from a Scientific American article. It's several decades old now, that basically tell us things that humans do and how they affect rates. So things that happen in the biosphere, whether it's fertilization and growth or deforestation, they happen fast. Right, they can be reflected in the atmosphere within a year or two of us doing it. And we can look back into the periods of time in the not so distant past when human migration started to go around in the various continents, and we can see this process happen. We can see it affecting climate. Things like how much CO2 do we put in the atmosphere and how fast does it dissolve in the rain and then transport to the ocean? It's also pretty fast. Things that are slow are the storage of carbon in the oceans into sediments by organisms making shells and falling to the seabed. Stuff's always happening, but it takes thousands of years to have a change in that show up in an overall change in the atmospheric cycle. And so what that does in essence is it allows us to calculate some rates of exchange, right? So gas goes between the atmosphere and the ocean over a time frame of about 1 to 2 years. Gas goes into more or less being stored as carbohydrates and other organic molecules in the biosphere over a time scale of 1 to 100 years. The rate at which deep sea sediments form and change is over sort of centuries to millennia, et cetera, et cetera. So that, and this is another IPCC report image, you can basically say, all right, let's just put a pulse of CO2 in the atmosphere and see how long it takes to redistribute into the 3 main places their CO2 goes. It goes into the atmosphere, it goes into the land biota, and it goes into the ocean. Right, and so here you can stick in a pulse, and then you can look over time how that pulse propagates through the system. And you can see here that over a 200-year time scale, start of the Industrial Revolution to now, there's like a subtle change, but most of it is still in the atmosphere. If you wait long enough, if you wait 10,000 years, which is like something like 5 overturns of the ocean, maybe 6, in its current configuration, eventually most of that CO2 is going to be in the ocean. The problem is we don't have 10,000. We're looking at what we're doing today, but I have full confidence that regardless of what we do today, over geologic time, this pulse of CO2 will, eventually modulate itself back. Okay, I've showed you this before, and a lot of that time scale is because of this, the rate at which the whole cycle churns, the oceans. So the last 2 slides kind of summarize this forcing of climate by the biosphere, superimposed upon by the kind of original variation, which is the thermal insulation coming from the sun. And so you can think about this different ways, but I think about like in the current ice age, not ice age period, is that an interglacial, a warm period is normal. Okay, I'm just going to call it that. And it's got high CO2 and high methane. That reflects a fully functioning biosphere that's cranking a lot of stuff. And then when you start to cool the planet because of the insulation, right, how we're orbiting around the sun, then the planet gets a little bit colder, we grow some ice sheets, it lowers sea level, it changes the carbon cycle and it pulls CO2 and methane out of the atmosphere. And it makes it colder than it would have been from just the solar insolation. Then we grow ice caps, and then something happens that relaxes this whole thing. And the relaxing, the thing that takes us from an ice age back to warm period, this happens really fast. Right? This happens slow. This is that thing that takes like 100,000 years to go from a peak of an interglacial into an ice age, and then all of a sudden we snap back. Okay, and there's a lot of discussion about what that snapback is and how much of it is driven by the biosphere or other things, but we are adding gases in a condition that's like a snapback to a time where we have already snapped back, right? Because we're already hot, but we're adding more gas. So the very last slide is something you can read on your leisure. It is a description of the same thing I just described, but in kind of more detail. I kind of highlighted some stuff in here. You know, I left the citation where I got this from. This is from the Habitable Planet, where the reading is for this week. This is from an earlier version of that book. But basically, Wally Broker's kind of explanation of, you know, how the relationship between biological proximity and insulation causes greenhouse gas. All right, so far we're just talking natural cycle. So does anyone have any questions about any of this? No?